Hello, Mr. Stevens here. It is April 20th. Today we were working on the assignment for today, the 20th and the 21st, which is using paper chromatography to kind of study polarity of molecules. So bear with me here, do a little bit explanation to
see I have some setup and things going here already, but in order to know what's going on here with the actual chemistry, we have to know conceptually what we're talking about. So we have been studying, or trying to study at least, hopefully you have been, the concept of polarity. So you can see here polarity is an uneven charge distribution due to different electronegativities. So if you forget that electronegativities, that refers to how strong an atom will be pulling on electrons. So really an electronegative, like fluorine, pulls on electrons, sorry about that, very hard. In a bond, it's pulling most of the electrons towards it. Something that has really low electronegativity, such as in group 1, any of those of the periodic table, they don't pull on electrons as hard, so that can influence this thing called polarity. So an example, which is almost easiest to see in examples, in polar bonds, you have really electronegative things to the right and up on the periodic table, like chlorine. If it's bonded to something that's less electronegative, in this example, carbon, so the chlorine's more electronegative, so it pulls the electrons that are in the bond towards it, so it becomes partial negative, because remember, electrons are negative. And then the carbon has, the electron density is kind of shifted this way, so that means that, the protons are more evident, and so you get kind of a partial positive charge here. Again, why that is, because this one's less electronegative, this one's more. Now if we look at, in this arrow before we move on, you can see this looks like a plus, so partial positive, and then the arrowhead is towards the more electronegative one, partial negative. Now nonpolar bonds, oftentimes the same atom bond to itself, and they have the same electronegativity. And as far as bonds go, if you have different atoms here that are nonpolar, they would just be very close in a periodic table or have very similar, if not the same, electronegativity. So we want to look at molecules, so obviously, because things exist in multiple bonds within molecules. So things like HCl, like H2O, water, and ammonia, NH3, are all polar. So that means they're uneven in their charge distribution. So here you can see chlorine is more electronegative than hydrogen, so it pulls electrons towards itself. So this results in a partial negative here and a partial positive here. So this molecule has poles, partly, like a north and south pole, but this one's partial negative pole, this one's partial positive. Water has these bonds that are polar bonds, and due to the shape, it's this bent shape, remember we talked about this, oxygen's more electronegative, so it pulls the electrons that are bonding towards itself. So that makes this partial negative side, and this is partial positive. So again, just like north and south poles, this one's partial negative, this one's partial positive. I'm going to represent the whole molecule's charge or polarity here with this red arrow. So I'm just going to go right up the middle in this way. That way you can see that the whole molecule has a partial negative charge here, has a partial positive charge on this end. So that means it is polar. And then ammonia is here as NH3, and you can see the polar bonds that make it up because nitrogen is more electronegative than hydrogen. So these little pluses, we have partial positives on the hydrogen because the electrons are being pulled towards the nitrogen. And so thus we get an overall polarity. I'll try to represent it here best I can with another red arrow, and we'll just kind of bring it up the middle. So partial negative, partial positive on this end. It's a bit of a simplification, but obviously the nitrogen is more electronegative, so it's pulling electrons, so it's partial negative up this way, and then down here, partial positive on the hydrogen ends. Again, just like water, it has a pole, a positive and a negative one. Two poles, actually. So nonpolar molecules, though, just like nonpolar bonds, Same electronegativity, so there's no imbalance in charge here. So there's no poles, non-polar. So it is just evenly distributed. There's no partial positive or partial negative. It just is nice and neat. Methane, CH4. So you can see there's polar bonds here, but you can have polar bonds, but if they cancel out, like this one and this one are equal and opposite, this one and this one are equal and opposite, that means they cancel, and there's no partial positive and partial negative part to this molecule. It's just equals out, and thus it's non-polar. Where's my pen here? So non-polar. There's no poles on it. It just is here. And this is common with organic things like hint oils and fats and things like that. And then CO2, carbon dioxide.
Welcome back. So to explain chromatography and what it is, it has two components. Generally you have a stationary phase. It's called stationary because it's a solid oftentimes, and that's the paper here, or cellulose if you're talking about chemistry. And then a mobile phase is a solvent, such as something like maybe rubbing alcohol, isopropyl alcohol, and or water, which obviously comes from the tap over here. So looking at the polarity, so isopropanol does have some non-polar parts here with these CH3 components, but it does have this oxygen, so in general it kind of has that polar attribute of the oxygen's pulling electrons towards it because it's more electronegative, thus it's a polar molecule. And then water, of course, has that polarity, which we've already seen, of pulling electrons towards it here. And if we look at cellulose, it falls under organic molecules, which generally have carbon, hydrogen, and oxygen, often are non-polar, and thus our paper is cellulose. So it falls into the non-polar category. So our stationary phase is the paper stays still, and then our solvent, or it's called mobile phase, is either just pure isopropanol or isopropanol and water. So taking a look at the action on the 100% isopropanol, so that's in the bottom there. And again, it's just touching the piece of, it's actually coffee filter paper. And I put drops, we have green food dye on the left, and then we have yellow food dye on the right. And then you put those in just so the very bottom of the papers touch the isopropanol, and then the solvent obviously climbs up the paper by way of capillary action, and it will separate the different components based on polarity. Okay, so if you want to see the setup up close, have a pencil with one of those clips holding onto the piece of paper, and then the covering is just to keep in any evaporating isopropanol inside of the glass there. So you can see the process here. This is blue food dye, was spotted on the stationary phase, so it means a spot was put on there close to the bottom, but you don't want it to be right at the bottom, so it would fall into the solvent, which is our isopropanol. So ideally my spot would be a little bit higher, but it is what it is. And then all you do is just put in your paper, and the goal is to get it to just touch the solvent, which is that isopropanol, but not stick the dotted substance in there. So I'm trying to see if it's touching or not. There we go. And I forgot to fold my corners. That's probably gonna influence it. But that's how you do. And then the solvent runs up, and then we'll move this based on the polarity, and we'll see if it has any different components more than just blue. While the 100% isopropanol is running with the red and the blue, and honestly it doesn't look like much is happening there in the way of separation. Prepared 50-50 isopropanol and water, and then added it to these jars here, and I'm going to be running the yellow food coloring and the green. So welcome back. So after we've done all of the running of the chromatography here with our pieces of filter paper, and then we put dyes on here, so yellow, green, red, blue food dye. You can see 100% isopropanol did a pretty good job of separating out yellow and green. Red is just red from, at least just from this solvent system,
Then blue had a bit of separation. I should have let it run longer, so sorry about that. And then the 50-50 mix of isopropanol and water. The green, again, had some separation, not as good as the 100% isopropanol. Yellow, there's a little bit of pink up here for separation, but kind of not so hot. Red is still just red. And then blue did some separation here. You can see there's this red pigment, and then I'm not sure if this is purple in the middle or what this is. And then it has kind of a blue arc up top. So it's basically our results, and more information to come. For a quick explanation here of like what happened in this setup of paper chromatography. So our green food dye was spotted around here, and then the isopropanol by capillary action went into the filter paper and traveled up, and as it went, it moved the different parts of the dye depending on their polarity. So those that are most like the isopropanol, which is pretty polar with an OH group, went as right along with it, and then maybe less polar stuck to the paper, and then the least polar or the most non-polar, again remember that's like the cellulose of the paper itself, didn't travel very far at all, like the yellow portion of this that you can see here. So that's kind of that quick and dirty explanation of the polarity in regards to this separation.